global demand for food produce is increasing. Many TV shows and news sources always speak of the difficulty that farmers face to produce high-quality food, often consuming time, money, and other unsustainable resources to keep up with demand. Smart technology is one of the only plans moving forward to improve farming. This video will focus on the design of a smart irrigation system that would enable a farmer to monitor the soil moisture content of plants and ensure optimal conditions for plant survival. This is an example of an embedded system design. If you haven't checked out our previous video introducing embedded systems, make sure to check this out first. Embedded systems require an architecture if we are to proceed with a design. Often, we use a bottom-up design principle where we first focus on the use and what is needed, not on individual component properties and requirements. Overall, we need a power source, some kind of sensor technology, a microcontroller which can interpret signals, then trigger actuation and data logging through the user interface. The next step is to consider a circuit block diagram. We need the power source to connect to all components to provide power. All power needs to be connected to ground to complete the circuit and prevent shorting. Some kind of voltage regulation needs to ensure that external factors such as temperature don't affect the power provided, so certainty is needed around powering the system. We may need different voltage levels at a later point depending on the exact devices that are chosen. There needs to be some kind of analog and digital exchange of information between the sensor, the water valve, which is the actuation in this case, and the transmitter, which will update the user of how much water is used and at what points in the day. Now for the sensor technology. If we have a capacitor and consider adding a dielectric, the electric field is affected, allowing more charge to be stored on opposite plates for the same voltage across it. If the dielectric changes, capacitance changes, so the voltage and current change will be measured as being proportional in some way to the water level. This can then be amplified using other circuit components, such as op-amps, to feed into the microcontroller. Once the working principles for the sensors have been considered, you can start to think about component selection by looking at data sheets, allowing you to progress with the design. There are some key considerations for this application. Temperature range is important here, as many plants are grown in greenhouses, but we don't want the electronics to break or introduce unwanted noise in these environments. Sensitivity is another aspect to consider. We may need to be able to notice small changes in the water level depending on how much precision is needed. Power consumption for each component needs to be analyzed. This is not as simple as looking at the datasheet, but values such as resistance and IV characteristic curves can help us to model how power is used so that the device can run efficiently. The microcontroller specification has other factors to consider, as it can have many functions that we may need. On the theme of power consumption, sleep modes can aid with this. Often microcontrollers perform sequences, but not everything in this sequence needs full power, so there are opportunities to save power. Analog and digital conversion can be inbuilt into microcontrollers, which is often easier than implementing separately. We may require PWM outputs to be available, as it is another area in which power can be saved. Memory considerations are needed to ensure that there is enough space available for the programming, data analysis, and control system. The type of memory influences the speed of operation, and precision is influenced by the number of bits that are available to represent numbers with more decimal places, which is affected by memory. Finally, the computing power needs to be appropriate. This is affected by memory type and power consumption, but also the number of cores available and the instructions per second that can be fetched, executed, and decoded. Additionally, the consideration of sequential versus parallel computation has a large effect on computation power. There are some final touches that are needed to get the basic system up and running, such as software for the microcontroller. Firstly, you need to consider if a high-level or low-level programming language is needed for the level of control required. The control algorithm is needed, which is often done by taking Laplace transforms to find the transfer function, then producing a block diagram with feedback. This is how you would implement a controller. Then the user interface can be considered, such as an app for a phone, so that the farmer can monitor their plants more efficiently. Iteration is essential in engineering design. Here, some considerations are needed, such as power efficiency, noise reduction, precision and speed, and then cost, manufacturing, and maintenance. Once the design is working, more features can be implemented to refine the system further. The future of farming relies on more sustainable and efficient practices, and this smart irrigation system is just a start. If you want to see more, please like and subscribe to support this channel.